All right, we're going to start at the bottom of this page where it says electrostatics, and it asks which pairs of charges attract, positive and negative attract, opposites attract, which pairs repel, negative and negative repel, positive and positive repel, or like charges repel. Difference between an insulator and a conductor. Insulators don't allow electrons to move easily. Been a while since I wrote with one of these pens. All right, don't allow electrons to move easily. Conductors do allow electron movement. Examples of insulators: plastic, glass, wood, concrete. Conductors, these are all the metals. Some are better than others, but all of them conduct. Ready for the next page? So here we go. In the drawing below, positively charged rod here held near an uncharged foil leaf electroscope. That means the electrons are going to move up from the bottom, and they're going to give the top of this thing a negative charge, which means the bottom is going to become more positive. So electroscope leaves, they're going to be positively charged. If we give a positively charged rod, number 4, so let's get some positive charges on there, near a neutral conductor, and they love having metal spheres. It means the electrons from this sphere are going to be attracted to the positive rod. It will leave the opposite side of this conductor slightly positive. Number 5, the electrostatic force between two charged objects is F. What is the force when the distance is doubled? Will you remember the formula? K, QA, QB over R squared. So if I double the distance, I'm squaring it. That means I'm going to get 1/4 of the force because the R is in the denominator. Change to 1/3, square it, I'm going to end up with 9 times the force. 3 times the original distance, I'm going to have 1/9. Wow, having a hard time making that a 9. 1/9 of the force. So if you just keep in mind that you're going to square the distance and that it has to be bigger if it gets closer, you should be okay with these. Number 7, this time we're going to have to calculate this out. And so we've got the force equals KQQ over R squared. K is 9 times 10 to the 9th. 2 microcoulombs, that's 2 times 10 to the negative 6, minus 5 times 10 to the negative 6, and that's all over 5 centimeters squared, which is 0.05 meters squared. Remember, you got to be in the right units. When you multiply this all out, you should get negative 36 newtons, which means that force is pulling them together, because I've got one positive and one negative. Draw the electric field charge near a positive point charge. So here's my positive. By definition, the field goes outward. And I'm not going to get too crazy with the lines. It's hard enough to draw with this pen. Negative field. Field goes inwards. We develop these fields using positive test charges. So repelled by the positive and attracted to the negative, and that's what the field shows. Next page. All right, so they'd like us to figure out what the force is on charge A, B, and C. A is going to get pushed down and away. Let's see, why am I not getting any luck writing here? There we go, down and away. B is going to be up and to the right, and C is going to have no net force. It's hanging out right in the middle where it doesn't feel any force at all. Number 11. I have an electric field, so that's big E of 2 newtons per coulomb. I have a 2 coulomb charge, so that's Q. And they want to find the electric force. So I'm going to use the equation E equals F over Q. Good heavens. So if I want F is E times Q, 2 newtons per coulomb times 2 coulombs gives me a force of 4 newtons, and they gave me a direction of east, so this will be an eastward force. Number 12, I got a 2 microcoulomb charge, a force of 5 newtons, find the electric field. So once again, E is F over Q. The force, 4 newtons, over the charge, 2 times 10 to the negative 6 coulombs. And then I'm going to have an answer of 2 times 10 to the 6th newtons per coulomb. Electric field strength, a distance of 0.3 meters from a 1 microcoulomb charge. So let's use the equation E equals K Q divided by R squared. That's an ugly looking square, but you got the words at least to go with it. 9 times 10 to the 9th is K, the constant. Q, 1 times 10 to the negative 6, since it's a microcoulomb. And the distance between them, 0.3, and we need to square that. Do the math. I get 100,000. I don't know, those are some ugly looking zeros. 100,000 newtons per coulomb. Off to number 14. Here they give us some charges and an electric field and a distance, and they'd like us to figure out the work and the potential difference. So I need to find work and I need to find voltage. Work is going to be Q times E times D. In this case, 3 times 10 to the minus 6 times 12 newtons per coulomb times the distance of 0.5 meters. And when I calculate that all out, 1.8 times 10 to the minus 6. And that's going to be joules because it's work. Now let's see if we can figure out a way to squeeze the velocity in here, or the voltage in here. The potential difference is voltage, work per unit of charge. So I'm just going to take my work number, 1.8 times 10 to the minus 5, minus 6, which is it? Should be minus 5. Let's make sure we got minus 5 there too. Negative 5 over here, divided by the charge of 1 times 10 to the, 3 times 10 to the minus 6. Keep track of your numbers, woman. And when you calculate that all out, you get 6 volts of potential difference. Off to number 15, and I'm going to go back to blue. 10 joules of work, an electric field, and a moving charge of 2 coulombs. Let's do V is W over Q, the work done per charge, 10 joules, 2 coulombs. I get 5 volts of potential difference. Potential difference, they want me to find if I have parallel plates with an electric field and a distance, so V equals ED, 2,000 newtons per coulomb, times the 0.002 meters, and I end up with 4 volts. Change in kinetic energy of a charge of 3 microcoulombs that moves between the plates. So change in kinetic energy is going to be the same as the work done. So I know that then I'm using V equals work per charge, or work equals V times charge. I have my voltage of 4 volts, and I have a charge of 3 times 10 to the minus 6. which should give me 1.2 times 10 to the minus 5 joules of work. That's it for this video. Next one's in another clip.